Good morning, all of you. Welcome back to the AWP sessions. So in today's session, what we do is we are going to start with unit number 4, which is antenna arrays, because that is the basic, that is a very important unit for us because we have problems in this particular antenna arrays, which are very, very easy. And the theory is also going to be very easy. So we have to compulsorily prepare this particular unit, which is unit number 4. Unit number 5 is totally theory. So for examination point of view, unit number 4 is very important. The concepts involved in unit number 4 are coming in unit number 3 also. Therefore, we first of all try to complete unit number 4. Okay, before we just deal with some of the topics which are left over in unit number 3. So therefore, first of all, we are going with antenna arrays. Well, so in the very beginning sessions, introduction to the antennas and wave propagations, I discussed about these various antenna arrays. So what is an array? Basically, array is something like collection of similar elements is known as an array. So here also in the case of antennas, we normally going to connect more than one antenna in an array to increase its directivity, to increase its radiation patterns, to increase its radiation strength. To increase its directivity, we normally use the array of antennas, just like cascading of amplifiers. So in cascading of amplifiers, why we use cascading of amplifiers? The cascading of amplifiers are used to increase the gain of the amplifier circuit. Here also we can increase gain of the antenna by just simply connecting them in an array fashion. Now, what kind of antennas can be used in the array of antennas? The examples of array of antennas are going to be Yagi wood antennas, microstrip patch antennas, aperture array antennas, slotted waveguide antennas. So all these are the various examples of array of antennas. So why we normally use them? As I was talking to you just now, use it for very high gain applications. Whenever we want more gain to be produced, the signals with more gain to be produced, then we normally prefer the array of antennas. So here mostly when needs to control the radiation patterns also. That means wherever we wanted to have more directivity, more radiation pattern, there also we normally going to prefer this particular antenna arrays. And what are the examples of antenna arrays which we have seen in the previous sessions? So we have seen about wire antennas like dipole antennas. We can use folded dipole antenna by constructing antenna array. That means two such dipole antennas can be constructed one after the other and forming a dipole antenna, a folded dipole antenna. Okay. So that means similarly we can just connect a similar circular loop antennas in series. Okay, to form an array of circular loop antennas. Similarly, rectangular loop antennas. Similarly, helix antennas also we can able to connect them. So aperture antennas, that means here these are all the aperture antennas, different types of aperture antennas that we have. That is pyramidal antennas, conical antennas, rectangular waveguide antennas. So these antennas are also can be connected in arrays. Monopole antennas also can be connected in arrays. Dipole antennas also can be connected in arrays. So like this, we can just form bunches of antennas, antenna arrays to increase its characteristics. Similarly, lens antennas also we can have various lens antennas can be connected in array fashion to construct all these things. And if you see this is nothing but a microstrip antennas, microstrip patch antennas, where all these are rectangular microstrip antennas. They are interconnected to increase its radiation characteristics. And here also we're going to have one more type of the microstrip patch antenna, which is going to be array, and all these small strips are going to be the rectangular microstrip patches. So all these patches are interconnected internally and will forming a antenna array. Now, what are the applications that we have that are going to be there that are used in the antenna that are used for antenna arrays? The applications are simply going to be the aircraft application. See this now. This is going to be formed with antenna arrays. My microstrip patch antennas are normally used in the antenna arrays for the aircraft signal receiving purpose. Reflector antennas can also be connected in array. So like this, we can normally going to form array of antennas. So in the practical applications, we normally prefer this antenna arrays, especially for transmitting signals to the satellite or receiving signals from the satellite, aircraft applications. Okay, all these things we normally going to prefer the antenna array. Now, what are the various types of array antennas that we have in the syllabus? We have around three types of antennas. That is going to be linear arrays, binomial arrays and planar arrays. So here we discuss about the, now we are not going to discuss in today's session about the mathematics involved in all these arrays. I just wanted to give an introduction to the array representation practically, and we are always going to treat the arrays as the point sources. That means, what do you mean by array represented by its point source? The array represented point source is something like same array whose dimensions are reduced to a level which is going to be very very small, where we represent them as a point sources, where we represent them as point sources. For simplicity purpose, we normally going to represent arrays and antennas as the point sources, and all these point sources are simply interconnected. Now the properties of various types of antennas are applied to these particular point sources of antennas to analyze the radiation pattern of the antenna. That is what we normally going to do all together in this particular type of the antennas. And here we have, most importantly, what is most important is, here we have a isotropic point sources. So what is the isotropic source? Isotropic source is an ideal source where the signal is going to get radiated in all the directions with equal strength, is known as an isotropic antenna or isotropic point sources. Okay, so array of two isotropic sources is what we have in the syllabus. And next one is going to be like principles of pattern multiplication. Now, one great thing is, how do we normally increase gain of the antenna? We normally increase gain of the antenna by a process called pattern multiplication. The antenna radiation is going to have some radiation pattern. So all these patterns are simply going to get multiplied, and the resultant value of these multiplied patterns is normally radiated from the antenna for the far field regions. So therefore, the pattern multiplication is going to be a very, very important concern for us throughout this antenna array propagations, throughout this antenna array wave propagations. So here we are going to have array of, we have in the syllabus arrays of two isometric sources. We normally do some problems on how do we represent these isotropic sources, and how do we find out the various patterns of the isotropic sources, and next how do we normally perform the pattern multiplication based on the principle of the pattern multiplications. And next types of arrays are going to be in the linear arrays and the linear arrays of n elements with uniform amplitude. So that means we normally going to collect n elements with uniform amplitude. That means n elements means what? N elements of the same type of antennas will be connected in the arrays. What is array and a set? Basically, array is normally going to contain similar type of the antenna. Set is normally going to contain dissimilar type of the antenna. So therefore, we use array of antennas. Means what? Similar set of antennas are normally used in the arrays to, in order to represent the antenna, in order to represent an antenna which is called as an array of antenna. So here we have, in the previous class, in the very beginning classes, we discussed about broadside arrays, end-fire array antennas, where broadside is nothing but what? The radiation pattern is normally be in a direction of the axis of the antenna. End-fire will be perpendicular, normal to the direction of the axis of the antenna. So that's what the basic difference which we have, that we normally going to have. And in this, we normally going to scan the array pattern of the antenna. And here we have linear arrays with non-uniform amplitude also. So that means the arrays are normally going to radiate with non-uniform amplitudes, are normally going to be there. So the next one is planar arrays and binomial arrays also there in the syllabus. So all these array configurations which we'll see in terms of the point sources. And I'll just wanted to give you a brief of what we're going to discuss in the days to come. Okay. So here we normally going to think about the finding out the electric field. How do we find out the electric field, resultant electric field of an antenna at a particular point on the spatial domain? Now imagine if two antennas, say point antenna 1, antenna 2, they are treated as a point sources. Now what is the effect of these two antennas at the point P in terms of getting the electric field? That means, what is the electric field, resultant electric field, because of these two antennas at this particular point P? that we are going to find out here in this particular unit. And what is the effective resultant phase between these two antennas? Okay, between the resultant phase difference between these two here at a point P, because of these two also we normally going to find out as phi, beta d cos phi, which we discussed in the earlier class. We represented this beta d cos phi in the previous class when we were discussing about the loop antennas. Okay, so next is we discuss about the radiation patterns, how the pattern, how the radiation pattern is normally going to be there with respect to 0, 60, 90, 180, 270 and 360 degrees. How the antenna is normally going to get radiated, and what is the resultant radiation pattern. So different radiation patterns are normally going to get resulted because of the area of antenna. That also we normally going to see over here. That is phi. Phi is the radiation angle inclination, and E is the electric field, value of the electric field at a point under consideration. So these topics we're going to cover in the syllabus. So this is what radiation pattern directions now: 0 degrees covering 0, 30 degrees and 60 degrees. It also in the reverse, because it is going to be a bidirectional antennas. Bidirectional antenna is going to have radiation along this direction as well as in the opposite direction. Therefore, it is called as a bidirectional type of the antennas. So like this, we normally going to discuss about how do we normally going to get the electric field, phase angle, and the radiation patterns. So this is what the discussion we normally going to do. Now, whenever we go with the radiation pattern of an array of isotropic radiators, how the radiations are normally going to take place. See here, the radiations are going to take place like this for the array of antennas. The resultant one is normally going to get accumulated at the particular point beyond the spatial domain always. So next one is going to be say some broadside area of antennas. So in the broadside area of antennas, how the radiation pattern is going to be there, and in the end fire type of antennas, how the radiation pattern is going to be there. Okay, and there we find out the beam beam with first null radiation angle. Also, we normally going to find out. And how does the directivity is achieved? How does the directivity is achieved when we go with the array of antennas? See here, this 1 2 3 4 5 6 7 8 9 10 are the various array of antennas connected in series. To form the array of antennas, we normally, when we form the array of antennas, we definitely going to increase the directivity of the antenna. Okay, so that means this is what the basic things which we normally going to cover in this particular unit. In the next class, we start with the mathematical representation of the isotropic antennas. Thank you very much for the today's session. Thank you very much for the today's session.